Okay, in this video we're going to generalize the notion of the rational numbers, and we're going to do that to any integral domain. So let's just think about how the rational numbers are really defined. So we can think of the rational numbers as a set of symbols a over b, and so here we've forgotten that 1/2 means, well, 1/2 of something. It's just a symbol 1 over 2. And so we're thinking of that rational numbers just as those symbols, but then there's an equivalence relation on that set of symbols. So a over b equals c over d if and only if they can be reduced to lowest terms and they're the same. But notice that's equivalent to saying that AD equals BC. For example, 1/2 equals 2/4, and that's because 4 times 1 equals 2 times 2. Now we want to extend this idea to an arbitrary integral domain, and doing that forms this thing called the field of fractions. So let's see our setup here. So we have D as any integral domain, and then to that integral domain we want to think about this following set S. So it's going to be all ordered pairs AB, where A comma B is in D and B is not equal to 0. So really this ordered pair is like the symbol A over B. And then we've got this relation on S. So remember, relations are subsets of the cross product, so I put this tilde as a subset of S cross S. That just means that it's a relation. And then it's defined in the following way. So A comma B is related to C comma D. In other words, A comma B tilde C comma D if and only if AD equals BC. So again, we're taking inspiration from what's happening up here in the rational numbers. So the next thing that we'll have to show is that this thing is an equivalence relation, but I'll do that before starting the proof of this main theorem. But once we know that this is an equivalence relation, we can start talking about its equivalence classes. So then we define the equivalence class with these brackets. So bracket AB is going to be the equivalence class of A comma B. In other words, it's all CD that is equivalent to AB. So just like we did equivalence classes earlier in the course. Now we're going to collect all those equivalence classes together into something called F sub D, and F sub D is the object that we're looking for. And so the big theorem that we're going to prove is that FD is a field, and it's called the field of fractions of D. And furthermore, it is the unique smallest field such that D can be embedded inside of F of D. In other words, it's the unique field that contains D as some sort of sub-object. Okay, so before we get going with this proof, let's go ahead and prove the following. So proposition, this is an equivalence relation. So notice this is an important thing to prove because otherwise we can't really define this fourth or fifth dot down here. So let's see the proof. So first we need reflexivity. In other words, we need A comma B to be related to itself, and notice that A comma B is related to A comma B because AB equals AB. And really that's all there is to it. And now the next thing that we need is symmetry. And now, so let's go ahead and suppose that A comma B is related to C comma D, but notice that tells us that AD equals BC, but now we can just rewrite that as BC equals AD, but then that's the same thing as C comma D is related to A comma B. So that's all there is in this case. Now the next thing that we need is transitivity. So let's go ahead and suppose that A comma B is related to C comma D, and C comma D is related to E comma F. And notice our goal here will be to show that AB is related to EF. So now let's recall what each of these means. So this means that AD equals BC and that CF equals DE. Great. And then our goal over there, notice that that means that AF is going to be equal to BE. taking that pink over there as inspiration, that means we're going to need to get something in terms of AF and BE into this setup. So I think there's probably a couple of ways to do this, but what I want to do is maybe I'll take this very first equation and I'll multiply it by F. So notice that's not going to really destroy any information because we know that F is not equal to 0, and we know that F is not equal to 0 because it's in the second entry. And then also I want to take this equation and multiply it by B. And then for the same reason, we know that B is not equal to 0, so I'm not destroying any information. And so now let's see why I want to do that. Well, notice this is going to create something A times F, and then this is going to create something that is B times E, which is exactly what we need. And then furthermore, this is going to give us B times C times F, but this is also going to give us B times C times F. So that's going to be like super important that we get kind of like terms in this so we can combine nicely. Okay, so let's see what this gives us. This gives us ADF equals BCF. Great. And then over here, we have BCF. Remember, integral domains are commutative rings, so I can commute things around. And then this is going to give me DEB. So the next thing I want to do is notice that equality is an equivalence relation. So in other words, it's transitive. So that gives me that ADF equals DEB. But notice I can maybe rewrite that in the following way. I have AF times D equals BE times D. Great. But then we proved in a previous video that there's a cancellation rule for integral domains. And in fact, we know that here that D is not equal to 0, so we can cancel it from both sides, which tells us that AF equals BE, which tells us that AB is related to EF, which is exactly what we needed. So in other words, this is an equivalence relation, which allows us to talk about the equivalence classes and the set of equivalence classes. All right, I'll clean up the board and then we'll get started with the proof of our main result. So now we're all set to cover our main result, and the first thing that we need to do is show that the addition and the multiplication are well defined. And that's important because we're working in a set of equivalence classes. So we'll cover addition first. But before we do that, we need to really think about how addition should be defined in the first place. And we're going to take inspiration from what's happening in the rational numbers in order to define this addition in the first place. Because in rational numbers, we have A over B plus C over D. That's not just AC that's not just A plus C over B plus D. That is AD plus BC over BD. Remember, you've got to find a common denominator. So that means that's how we're going to define addition in our field of fractions. So in other words, we'll have AB plus CD equals, so notice this first entry is like the numerator, the second entry is like the denominator, so that's going to be AD plus BC over BD. So that's how our addition is going to be defined. So we want to check that that is well defined. So that means we want to take an element in FD that might have two different names and show that regardless of which name you use, you get the same quantity when you add them up. So let's go ahead and suppose that AB is equal to, maybe we'll call it A hat, B hat. So what that means is that A, B hat equals A hat B. So recall, because that means that these two are related in S, but being related in S means that this happens exactly. Okay, and then the same thing, we'll do the same thing with C comma D. So we'll say C comma D is C hat, D hat, but now notice that's the same thing as saying C, D hat equals C hat, D. So they're related via the equivalence relation. Now what we want to do is make this addition on both sides and make sure we get the same thing. So notice we have AB plus CD. So that's going to be the same thing as AD plus BC, comma, BD. That's how we're defining our addition. But now we want to look at what's happening in the hatted world. So we'll have A hat, B hat, plus C hat, D hat. So notice that's going to give us A hat, D hat, plus B hat, C hat, comma, B hat, D hat. And what we want to show is that those two are equal to each other. So let's point that out. This is our goal. Great. So now we can check this by taking this object multiplied by this object versus this object multiplied by that object, and you should get the same thing because again that is built off of our equivalence relation. So let's go ahead and do the pink objects first. So notice those product of those pink objects is AD plus BC times B hat D hat. Great. So notice we can multiply that out. That gives us A B hat D D hat. Great. And then plus B B hat C D hat. Okay? Now we can go ahead and use our equivalence relation to rewrite this and this using these two rules up here. So notice we can rewrite that thing as A hat B D D hat plus B B hat C hat D. Great. But notice we can factor a BD out of this. So that's going to give us times BD. So let's see what happens. We have A hat D hat plus B hat C hat. But that's exactly equal to... So what's left is we want to show that FD is the smallest field such that D lives inside of it as a sub-object. So in other words, we can include D inside of F of D, and this hook arrow means like it's an injective ring homomorphism. Okay, so this is pretty easy to start with. So we want to find a ring homomorphism from D to F of D, and we really want to again take inspiration from the rational numbers and thinking that the rational numbers are the field of fraction of the integers. And how would we put Z inside of Q? But we would do that by taking n to n over 1. That's an obvious inclusion of Z inside of Q. Okay, and the same thing is going to go here. So we want to consider this map, which I'll call iota, and it's going to go from D to F sub D, and it's going to take an element A, and it's going to send it to the equivalence class A, comma 1. So let's go ahead and show that this thing is a ring homomorphism. And then we'll show that it's injective. So let's say iota A plus B. So that is going to be A plus B, comma 1. But then using our addition rule, if we have a denominator of 1, this is actually pretty straightforward. This is the same thing as A, comma 1 plus B, comma 1. So you can check that that works with our addition rule that we have. But that's exactly equal to iota A plus iota B. So we've got the addition component for the ring homomorphism. The next thing we want to do is check the multiplication component, which is even easier. So let's look at that. So iota A times B, so that's going to be equal to A times B, comma 1. But then again, using our multiplication rule, that's going to be the same thing as A, comma 1 times B, comma 1, but that's equal to iota A times iota B. So that makes this a ring homomorphism. Now the next thing that we want to do is to show that it is injective. And so let's recall that a ring homomorphism is injective if and only if the kernel is the 0 element. So let's go ahead and suppose that iota A equals 0. In other words, that's the same thing as supposing that A is in the kernel of this homomorphism. But what that tells us is that A comma 1 is equal to 0 comma 1. Remember, that's the additive 0 element within f of d, but now by our cross multiplication rule, in other words, our equivalence relation over here, that means that A is equal to 0. But if anything in the kernel is equal to 0, that tells us that the kernel of this thing is just the 0 element, which is the same thing as saying that this thing is injective. Remember, showing the kernel is trivial is a tried and true way of showing that something is injective. Great. So we can include D inside of f of d. So in other words, this integral domain D lives naturally as a sub-object of its ring of fractions. Now the next thing we want to do is show this uniqueness. So it's the unique smallest field that D can be included inside. Okay, so let's do that. So we just got done showing that D can be included inside of its ring of fractions. Now we want to show that the ring of fractions is the smallest field that you can do that with. And again, we're going to take inspiration from the integers. So the integers can obviously be included inside the rational numbers, but they can also be included inside the real numbers. But what makes the rational numbers the smallest is that we also have an inclusion of the rational numbers within the real numbers. That's what makes the rational numbers smallest, because we can fit them between the integers and the real numbers. So that's the idea here. So let's sketch out this idea and then we'll look at it. So our idea is to suppose that we have a field K such that D is included inside of K via some homomorphism phi. So in other words, here we have phi is an injective ring homomorphism. Great. And then what we want to do from this is show that we can always fit f sub d in between D and this field K. In other words, our goal is to find some psi from f d up to K such that, so let's see what we have. We'll have such that the following diagram is completed. So we have D is going inside of f sub d, which is going inside of K, and now this thing is psi, this thing is iota. Great, and then these should compose to give us phi. So in other words, what we have going on here is any inclusion that we have from D into a field K can be broken up through this field of fractions. Just like an inclusion of Z into the real numbers can be broken up through this field of fractions, which are called the rational numbers. Okay, so let's see how we would maybe do this. So it's a little bit tricky to see what this psi should be, so I'll just write it down. So we're going to set psi of, so notice it has to start at the field of fractions, which means its inputs are these equivalence classes, and it needs to end up in K. We don't know what elements of K look like. We do know that some of the elements of K look like things from this integral domain D. So what we're going to do is think about this A as the numerator and this B as the denominator. And we're going to write this as phi of A times phi of B quantity inverse. Okay, so now let's talk about this. So recall that this object here, bracket AB, is made up of elements from the integral domain. So here we have A and B are inside of the integral domain. Great. But the integral domain can be included into the field via phi. So that means phi of A and phi of B are inside the field. So phi of A, phi of B are in the field. Great. But then phi is 1 to 1, which means since B is never 0, phi of B is never 0. But that tells you that phi of B has an inverse, because phi of B is a non-zero element from the field. So that means that this definition makes sense, if you will. Okay, so the last thing that we need to check is that psi is an injective field homomorphism. And so what that will do is that will put a copy of f of d inside of k. And then we need to check one more thing after that, and that is that this diagram makes sense. In other words, we need to check that, let's see if we can get this right, psi composed with iota equals phi. So I'm running out of room, so I'll bring that up and then we will check these details. So we just proved that D, the integral domain, can be included inside of its field of fractions. Now the next thing we want to do is show that if D can be included inside another field, that inclusion can be factored through the field of fractions. And so that makes this thing some sort of canonical object. In other words, it's like a smallest field containing D. Okay, so I've sketched this picture out. So we have D is being included inside of a field K via phi. And so we want to factor through this f sub D. So in other words, we've got this inclusion of D inside of FD. And then we've got this map, so we want to create this map psi from FD to K in a way so that when we have phi going from the very beginning to the very end, we have these two directions being the same. And I should say we define psi in this way, that psi evaluated at bracket AB is equal to phi of A times phi of B inverse. Okay, so we have two things to check here, and the first one is that psi is an injective field homomorphism. In fact, all non-trivial field homomorphisms are injective because the kernel is always an ideal, but the ideal of a field is always trivial, or the whole thing anyway. Okay, so let's go ahead and see how to do this. So let's do the addition. So we'll have phi of bracket A, B plus bracket C, D. So we know how the addition happens within that field of fractions. So that's going to be psi of AD plus BC, comma, BD, like that. But notice that is going to be equal to phi of AD plus BC times phi of BD inverse. But now we can use the fact that this is a homomorphism, phi itself, remember that's kind of like built into our assumption, that we have phi is this inclusion here, which is a homomorphism, and so we can write this as phi of A, phi of D, plus phi of B, phi of C, like that. Okay, great. And then this is going to be multiplied by phi of B quantity inverse times phi of D quantity inverse, like that. So now notice that when we distribute this onto the first term, the D part is going to cancel, and that's going to give us phi of A times phi of B inverse. And then when we distribute this onto the second term, the B is going to cancel, and we're going to be left with phi of C, phi of D quantity inverse. But notice that is exactly equal to psi of A, B plus psi of CD, which is exactly what we want to show for this to be a homomorphism with respect to addition. Okay, I'll go ahead and clean this up and then we'll look at the multiplication. So we just showed the addition part of the field homomorphism. Now we want to show the multiplication part. So let's go ahead and look at psi of AB times CD. So notice that's going to be psi of ACBD, like that. But now notice that that is equal to phi of AC times phi of BD quantity inverse. But now we can use the fact that phi is a homomorphism already to write this as phi of A, phi of C, and then phi of B quantity inverse, phi of D quantity inverse. And I'm using a little trick there which you might have to check, and that is we cannot bring the inverse inside of the homomorphism here because D is an integral domain. We don't know that everything is a unit. So there is something a little bit to check there, but it's not too hard, so I'll let you guys do it. Now the next thing we want to do is move some things around. So notice that is phi of A, phi of B quantity inverse, phi of C, phi of D quantity inverse, like that. But this is exactly equal to psi of A, B times psi of CD, which is exactly what we want to show for the multiplication part of this being a field homomorphism. Now the next thing I need to do is show that it is injective. Really, we've just shown that it's a ring homomorphism. Once we show it's injective, it will be a field homomorphism. Okay, good. Let me clean up the board and then I'll do that. Now we're ready to show that this thing is injective. So let's go ahead and suppose that A comma B is in the kernel of psi. And we want to show that that means that A comma B equals the 0 element. In other words, the kernel is trivial. In other words, this thing is injective. So now this tells us that psi of A comma B is equal to 0 in K. But that tells us that phi A, phi B quantity inverse equals 0. Okay, good. But we know that this guy is not equal to 0. Given that phi is injective, that means that phi of B is not 0, which means it's invertible. So that means we can multiply by phi of B, and that gives us phi of A equals 0. But then again, like I said, phi is injective, which means that the kernel is trivial. In other words, A equals 0. But that means that our original element was A comma B. But that means our original element was 0 comma B, but 0 comma B is the same thing as 0 comma 1 inside of FD. But what that tells us is the kernel of psi is trivial. In other words, it's 0 comma 1, but the kernel being trivial is the same thing as psi being injective. Okay, so we have psi being injective. The next thing that we want to do is show that the composition works this way. So we're almost done. We've shown that psi defines an injective field homomorphism from FD to K. Now the next thing we want to do is show that psi composed with iota equals phi. So let's sketch that out. So we want to show that phi is the same thing as psi composed with iota. Okay, great. So hopefully that's not too bad. So notice we'll do psi composed with iota, and then that operates on something from D. Okay, so we'll take our element from the integral domain just to be this A. So notice that this is equal to psi of A comma 1. That's exactly how we defined our inclusion. But that's going to be equal to phi of A, phi of 1 inverse. But then you can check that phi of 1 inverse is just 1 itself. So here we get phi of A. But now, since A was chosen to be arbitrary, we have psi composed with iota equals phi, which is exactly what we needed to do. So in other words, if we have some homomorphism from D to a field, it can always be factored through the field of fractions, making the field of fractions the unique smallest field that D can be included inside of. Okay, we're done.